Hello, let's have a look at binary patterns. Most of the time with Tidal we use patterns of numbers, either whole numbers or floating point numbers, decimal numbers, or strings, that is words, things like names of sounds and things. There's another nice type of pattern called a binary pattern or a Boolean pattern, which just contains either true or false values. And these can be really nice for controlling other patterns. So let's have a look at these with focus on two functions that use binary patterns, sew and stitch. Not in that order, but let's have a look anyway. So let's start with a simple example, one that's just using struct. So here is a pattern of just a single snare sound when a cycle, but I'm restructuring that with the struct function, which stands for structure. And whenever there's a t value, i.e. a true value, the snare will sound. So there should be 1, 2, 3, 4 per cycle. So straight away you might wonder what's the point of the false ones, because you can't hear them. And indeed, if it would sound the same if I replaced these with rests. So what's the point? Well, I suppose the point is that the false values can become true values by inverting the pattern. So if I use this invert function, or just inv, then all the falses will become trues and all the trues will become false. I could do every 3 inverts, so then you'd hear the difference. So I guess it's kind of true. There's no point using the false values until they become true again. Okay, so let's put that back. All right. So this also works with Euclidean syntax. So here I'm using this to make 3 true values over 8 steps. And again, I can invert that if I want. So in this case, when I'm inverting it, it's actually creating 5 events per cycle instead of 3, because it's taking all the ones which were empty spaces represented by false values and swapping those to true. So yeah, we can have a look at these as well. So this is what the true one looks like, 3 per cycle. I'm just using the letter A. If I invert it, then you'll see it fills them in the other way. So all the ones that were empty and now have an A in. And actually there's another way of doing this. So instead of making a pattern of true values, you can just start off by making a pattern of false values. So that's like doing an inverse of the true values. You're making a pattern of false values, and then the gaps in between them is where the true ones end up. You can hear that as well. So that is exactly the same as doing this. If you invert a true value, it becomes false, and if you invert a false one, it becomes true. So you're just flipping and flopping around here, or I am anyway. I don't know about you. Right. So let's have a look at this stitch function I mentioned earlier. So a nice thing to do is to have one sound doing the true values and one sound doing the false values. So here I'm structuring this with a 3/8 Euclidean pattern, taking the true values and doing the opposite for the snare, so taking the false values. So you can hear it's all filled in. All 8 steps are now filled. 3 of them with kicks and 5 of them with snares. And what Stitch does is does that for you. So you only have to put the Boolean pattern once with the true values in this case, which is what the kick gets, and the snare will get all the others. So it'll structure this as well, but with the inverted values. So that is exactly the same as this, just shorter, which is always good. You can, by the way, I'm making a pattern of sound, like control values here, but you could, that is actually slightly wasteful. I don't like typing when I don't need to. So instead of doing that, I could make stitch the words instead, and then just make that the sound. And so it's like I'm applying the stitch inside the sound pattern to the words that are there. I'm on a lower level here with the stitch, working with patterns of words and then just turning the pattern of words that comes out of the stitch into the sound pattern afterwards. Slightly quicker way of writing that. I do talk about that later in this file. So, right, so you can also pattern these Boolean patterns in just the same really as any other mini notation pattern. So you do get the repetition after a while and sort of lock into it. But here the number of steps that are filled in skips between 3 and 5 for the kick. Of course, this is getting the inverse, so this is instead getting the other 5 and then the other 3 values that are left over. But I'm also patterning the skipping that's happening here. So here this skips, sort of cycles it by 2 steps, and here by 3 steps, then goes back to 0. So it's kind of shifting the pattern as well. So you end up with quite a complex sort of movement between the kicks and the hi-hats, the closed hi-hats in this case. Here it's even more complicated because it's shifting between 8 steps per cycle to 6. Pretty weird. And yeah, and that's where, again, I'm doing the stitch inside the sound, but it'll just sound the same. Okay, you could also alternate between true and false here, while also applying the Euclidean pattern, as you can see. So there's 3 A's here, and then there's the 5 other ones here, and it skips between those. So let's listen to that. So with a struct, we've got the true and false, and we've got the 3/8 pattern. So you're getting the kind of inverse pattern every other cycle. Good. Oh, and you don't have to use TF. If you prefer to use 1 and 0, then that also works exactly the same. They're just aliases, whatever you prefer. So, and you don't have to use Euclidean syntax either. As you saw at the start, you can just manually write out the T's and F's. And you can use the MIDI notation as normal. So instead of repeating the T, I might do that. Maybe repeat it more, maybe. It could also be polyphonic, so I could do this sort of thing. I've made a mistake there though. I think it was there. So on. And of course, add on extra effects. Always good to have a bit of reverb. Okay, so that's Stitch. A synonymous one that works quite differently is So. So with Stitch, all the rhythm is coming from the Boolean pattern. With So, it works more or less the same, except all of the rhythm comes from the patterns that you're sewing together. So this is a bit of a gotcha. So here I'm skipping between this pattern and this one. So the first half is this pattern and the second half is this pattern. But there's a problem. Because in the second half of this pattern, there's no new events. The clap has already happened at the start when we were listening to the kick. And when you get to the second half, there's nothing there. Just empty space, so nothing sounds. To be able to hear that clap, I'd have to shift the start of it to the second half. But then I could do things like so now I don't hear that snare at all until I change this. Then I don't hear the kick. Yeah. So you can manipulate the So to switch between the two patterns, but you don't hear anything unless there's actually something there. Let's try this. Yeah. It gets a bit confusing because you've got to think about the structure of this and the structure of this to get what you want, or you can just play around with it until you hear something you like. So that's just explaining that. But so really comes into its own when you've got more complicated patterns. So I've just made a couple of more complicated patterns using the CPU and the second CPU sample bank. So let's have a listen to them individually. Okay, that was the first one. Let's listen to the second one. So kind of similar, but without the chunking that's going on and with a bit of distortion on. And now sew them together. So here I've got just true and false, skipping between those. But I'm actually using iter4 on that. So that true and false is shifting by a quarter of a cycle every cycle. That's nice. It feels like they're kind of blended together in an interesting way. Just shifting, picking sounds from one pattern or the other, and it kind of makes a new rhythm out of it. I like it a lot. Okay, so that's sort of introduction to binary patterns. There's more you can do with this, but I'll follow that up with another video. So take care.